This is still 4.5. We have not finished 4.5. We have these two models to work on. Exponential growth. The model is A of t equals A0 e to kt. I will explain each and every piece. This is from before that we know. Amount of bacteria, amount of birds, number of fish, number of mice, rabbits, etc., etc. Amount or number at time t. At time t. A sub 0, of course, is the initial count, the initial number, birds, rats, people, whatever. K is the growth rate. T is time. Okay, so let's look at our first example. Okay, so let's look at problem 8 on page 529. I take notes when I read. They say in the year 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. By 2050, it is projected to grow to 12 million. Use the exponential growth model, this one, and it's given to us, in which t is the number of years, t, number of years since 2000, to find the exponential growth function that models the data. That's part A. And then when we are done with this, we'll go to part B. Okay, so there was a census. Yes, which one? Ariel, go ahead.
No, I just didn't know what you wrote down was at 3.2.
3.2 million and 12 million. Sorry about that.
Okay.
Okay, so in the year 2000, the census said 3.2 million. The population is projected to increase to 12 million by the year 2050. We're asked to find the model. T is the number of years since 2000, and we're asked to find the model. Which model? This model. So this is the function. This is what I don't have, and this is what I don't have. These are my variables. It's a function of t. A sub 0 is the initial value. It's a number, I have to determine it. K is the growth rate. It's a number, I have to determine it. Everything else is fine. So therefore, I'm looking at the information I'm given. I'm told that t is the number of years since 2000, then it means that t for this year, t is good. And for this year, t is excellent. Perfect. So what are we given in this problem then? Yes. In other words, we are given, what is this? Points or ordered pairs. Can anyone give us the point? Which of these two variables is the independent? Which of these two is the dependent?
3.2 is
the dependent. Very good. So 0, 3.2. What is the second point? 50, very good. This is what we are given in this problem. We're given 2 points or 2 ordered pairs, 0, 3.2, and 50, 12. Excellent. Okay, so here's the model. So let's use the model and write an equation for each point. What will you write for this point? Please dictate. What is this for this point?
Okay.
What? How much? So what is a of t for this point?
0.
That's the independent variable. It cannot be a of t. That is the dependent. This is the function. So then what is the function for this point? Correct. 3.2 equals, we do not have a sub 0, times e. We do not have k, but we have time. What is the time here for this point? Excellent. So we put the point into the model. I would like you to dictate the second point and put it in the model, please. Yes, go ahead. Anyone? 12 indeed equals a0 I don't have. E to k I don't have, but how much is time now? 50. So we used each point into the put them into the model, and now let's see what we have. Since we have two equations, we should be able to determine both variables. We should be able to determine the a sub 0, or the initial count of people, initial number, and we should be able to determine the growth rate, because we have two variables and two equations. How much is k times 0?
0.
How much is e to 0?
1.
1. So then how much is a0 then?
2.2.
Exactly. Million. Did we need to do this? No, but I wanted to prove to you and show you that that's how we plug in the points into the model. Good. So I already determined the first unknown, so I'm going to replace this in the second equation and then solve for k. So we have 12 equals 3.2 times e to 50k. This is the second equation after I replaced a sub 0 by 3.2. Now we have to think, what type of equation is it?
Exponential.
Excellent. We have to clean it up first. How do I clean this up first? Of course. 12 divided by 3.2 equals e to 50k. Only now I can apply that procedure that solves the equation. What procedure am I referring to? Excellent. Natural log to both sides. So the natural log of 12 over 3.2 equals 50k, and from here I get k. When you're ready, tell me what to write.
Oh. Natural log.
Yes.
Minus natural log.
No. This over this. So let's plug it in the graphing calculator. And I didn't use the calculator with the previous class, so as you see, I'm not ready. Sorry. Here it is. So let's put natural log of 12 over 3.2. Don't forget parentheses. Natural log 12 divided by 3.2. Close the parenthesis and divide by 50. And the answer is, and we have to use at least 4 decimal digits for the rate, for the growth rate, 0.0264. So k is approximately 0.0264. And now I can write the function, the model, a of t equals 3.2 times e to 0.0264 t. Now we know everything about the model. There is a part B in this problem. In which year will the Palestinian population be 9 million? In which year the population will reach 9 million? What do I need to do next? Say it again.
You replace 9 million with E.
Replace what?
E with 9 million.
You mean this one?
Yes.
No, that's the base of the exponential function. I can't change that.
So you're estimating.
The 9 million for A.
Which one? So what do we do? Anyone other than Heather? She's punished? She didn't eat candy? No, I'm kidding. So what do we do? Anyone? Please.
9.2 for AT. Plus AT.
So it says, when will the population be 9 million? When? What do we need to do? If we look back at the points, can anyone read what these mean? Can anyone read this? What does this mean? When time is
50.
50, what is this? The what? Right. Excellent. So now the question is, when will the population reach 9 million? So what do we need to do? For exactly. That's all I need you to say. Excellent. Of course, the variable, the dependent variable is number of people. That's A of t. We are told when, find time t. Find t when the number of people is 9 million. Excellent. So what do we do next? It's not cleaned up. It's not ready for something that we have to use here. What do we need to do? By? Excellent. 9 divided by 3.2 equals e to 0.0264 t. What now? What do we need to do? We need to apply natural log. Very good. So the left-hand side is natural log of 9 over 3.2. The right-hand side is 0.0264 t. So we determine t dividing this quantity by this quantity. So natural log 9 over 3.2 divided by 0.0264. So let's put it in. Any questions? Any questions? Okay. So then we have natural log. In parentheses, 9 divided by 3.2. Close the parenthesis and divide. And I'm going to divide by the previous answer because I don't want to put it in. And it's right there. Okay, so 39. What does 39 mean? What is this? So t is approximately 39. What? Years since. Very good, which means the year 2039. Very good. Any questions? Any questions? Okay, I want to add a question here. So here's part C that I'm making it up. When will the initial population double? When will the initial population double? I'm going to copy the model on this page. You don't have to copy it again. When will the population double? What was the initial one? 3.2. What does it mean double? Very good. So now I want to determine not when the population is 9 million, but when will the population double, which means 6.4. How do I solve this? Excellent. That's all I want you to know, to say. Very good. And I will determine the time needed for the initial population to go from 3.2 to 6.4. In other words, how long it needs to double. Good. What type of equation is it, and what do we do? How do we address this?
It's the exponential equation.
What do we need to do first? Very good. So I know the answer. It's 2, right? E to 0.0264t. What now? Good. So natural log 2 equals 0.0264t. So then t equals natural log 2 over 0.0264. Okay. So let's see how many years since 2000 this population needs to double. So natural log 2 divided by 0.0264, and I got 26. 26 what? What does it mean? 26. What's 26?
26.
26 years since 2000, which means which year approximately? 2026. So please remember this kind of question, and we're going to get to more in a minute. So we will be asked to determine when will the population reach such and such, or when the population will double, or when the population will triple. What if the question says, when will the population triple? What will you do? What will be the only change here? Instead of, you will have 3. So that's the only change. So if I want to quickly determine that, I would just go back and say, and copy what I had and overwrite 2 by 3. And it will be in about 42 years. So it doubles in 26, but it triples in 42 years. Okay, is that idea clear now? Yes? Okay, perfect. So let's move on to the last model, and then we can go back and review. Let me see if we have on this handout, if I chose here anything with the exponential growth model, and just practice with that right away with another model. If not, we'll find more problems in a minute. Yes, there is one. Here it is. On page 6, problem 15. Problem 15. Do you all have this handout? Can we have this handout? Heather, can you pass this to Kendall? Yes. Sorry about that. Okay, ready? So let's do just that. Here it is. The exponential model. I don't like this with the fact that they don't put A of t. So I'm going to put A of t. A of t equals 543.3 e to 0.02 t describes the population of a country in millions. So there's millions. Okay. T years after 2003. T number of years since 2003. What is T for 2003 then? 0. Perfect. Use the model to determine when the population of the country will be 733 million. When will the population of this country, assuming the model still holds, when will it jump to 733 million? What do we need to do, and what will you tell me to write? Say it again. Yes, so please dictate and I'm going to write it. Anyone?
733.
Of course, that's all I want you to hear. 543.3 e to 0.02t. Awesome. That's all I needed. Then what? Of course, I have to get it ready for natural log. I can't apply natural log in this case. I mean, I could, but it's messy. It's easier if I simplify first. Okay, so now, indeed, we apply natural log. So natural log 733 over 543.3 equals 0.02 t, and then I can determine t. It's the left-hand side of a 0.02. So natural log of 733 over 543.3. Please make sure you put parentheses around that fraction. So natural log in parentheses 733 divided by 543.3. Close the parenthesis and press enter. Oh, I'm sorry, divided by 0.02. I got roughly 15. 15 what? 15 what? Yes, which means what year is that? In the year 2018, because we had to add 15 to 2003. Perfect. So that's the logistic, I'm sorry, this is the exponential growth model. Last model, the exponential decay. It's not different. I like to use this notation, it doesn't matter. The mass at time t equals the mass, the original mass, the initial mass, e to negative kt. Where this is not amount, but it's mass of radioactive substance. And this is not count, but initial mass. And K is the decay rate. Rate and T is time. Okay, so we are on page 530 now. All these problems have already one item that I haven't presented yet because I don't want to present it before I show one more problem. Yeah, they all have the same thing over and over. Okay, well, I have to present the half-life. I can't find an example for us to work on without the half-life. So all the problems in the book have the half-life. So let's talk about the half-life. I wanted to show an example before talking about the half-life, but there is no way. I can't find an example. Unless I have one here. No, I don't. I don't. Okay. So I hope you remember a few minutes ago, we were looking at the exponential growth model, and I said how long it takes for the population to double. Okay. Now, when we talk about the exponential decay model, we're talking about mainly radioactive substances. For example, radioactive substance decreases its mass in time. And the time needed for any amount to become half of it is called half-life. So half-life, if the half-life of a radioactive substance, let's say, is 10 days. If we start with 100 milligrams today, what will happen in 10 days? So after 10 days, we get 50 milligrams. What will happen? And after another 10 days, we'll go to 25. What will happen after another 10 days? We will get 12.5, and so on and so forth. So the decay rate is again we don't know what the decay rate. The half-life of this particular radioactive substance, or any substance, is the time needed for it to decrease its mass by half of the mass that we have. So knowing that, let's start with our first problem. A bird species, that's number 32, on page 530. A bird species in danger of extinction has a population that is decreasing exponentially. So, of course, we have A of t. I'm going to write the model one more time here. A0 e to negative kt. The one I prefer is m of t equals m0 e to negative kt. But this is for the radioactive substance. This is better for the number of birds. So that's a possibility. So let's use that. 5 years ago, the population was at 1,400. So 5 years ago, the population was 1,400. Today, only 1,000. Today, only 1,000 birds are alive. Once the population drops below 100, the situation will be irreversible. Then, when will this happen? So if it drops under 100, they will never recover. They will eventually die. If the trend continues, which we hope it's not the case, but okay. So basically, I did find a problem without half-life just yet. Good. Okay, so 5 years ago, 1,400. Today, 1,000. What are these? Points, right? Exactly the same thing we just looked at. Points. Okay. So we can reference everything to 5 years ago. So we can say this is x equals 0, or t, time equals 0, and then this is time equals 5. Right? 5 years ago represents time equals 0. And today, time equals 5, 5 years later. So then we're given two ordered pairs. Can anyone give us the two ordered pairs and make sure that the independent variable is time and the dependent variable is number of birds? Yes, 0, 1,400. And the other one is 5, 1,000. We are given the model. We have to create the model. So the question is, what are we missing? Well, A0 and K. And then we can determine when the population drops or gets to 100. So we have 2 points. We have to write 2 equations. Can anyone help with those two equations? No, because we're talking about birds. We're not talking about the mass of a radioactive substance. They are the same. The notation is not important. You use the notation you like. I don't really mind either one. If you like A, use A. If you like M, use M. But M stands for mass for the radioactive substance, and A is for number or count. So we have two unknowns. I need two equations because we are given 2 points. So can anyone give us the first equation? Don't solve anything. We would like everyone to see the equations. Yes? Excellent. 1400 equals A0, which is for now unknown, times e to negative k multiplied by? Awesome. Don't do anything to it. We just need to see it for now. What about the second equation? 1000 equals A0 e to, of course, negative k, but this time times 5. Excellent. Let's go back to the first equation. We have negative k times 0. What does that mean? Negative k times 0 is 0. E to 0 is 1. 1 times A0 is A0. So then the initial value, as we expected, is 1400. So then the second equation now becomes 1000 equals 1400 e to negative 5k, where k is the decay rate for the number of birds. It's not an increasing rate. Good. So then what? What will be our next step? Divide both sides by? Very good. So 10 divided by 14 equals e to negative 5k. Excellent. What now?
Log.
Very good. Awesome. We apply natural log to both sides. The left-hand side is natural log of 10 over 14. The right-hand side is negative 5k because natural log e is, can anyone remind us what is natural log e? 1. That's why it disappears. So then k equals natural log of 10 over 14 divided by negative 5. We put in the graphing calculator. So natural log 10 over 14 and divide by, in parentheses, negative 5. So the answer is 0.0673. 4 decimal digits. So approximately k is 0.0673. Okay, so then we have the model. The model is A of t equals 1400 e to negative 0.0673 t. If the trend continues, we would like to know when the population will be 100, because we know if we don't do anything between now and then this species of birds will disappear.
1000 equals.
So it says 100. One more time.
100.
Once the population drops below 100, the situation would be irreversible. When will that happen? So what we need to do?
100 equals.
Yes, 100 birds equals 1400 e to negative 0.0673 t. Great job. What next? As you see, it's nothing different from the previous model. The only difference is, and the models will be given to you, the only difference is this, the negative sign in front of k. So yes, we have to simplify, and we have 1 over 14 equals e to negative 0.0673 t. And what we have to do next? Yes, natural log of 1 over 14 equals negative 0.0673 t, and therefore t is natural log 1 over 14 over negative 0.0673. So let's see, when could this happen? We hope that's not the case, but we need to know ahead of time. Natural log of 1 divided by 14, and further divide by, in parentheses, negative 0.067. It was 29 to be exact. Okay. So 39, roughly. 39 what? $39 what? Very good. But actually, only 34 years from now. Because the count and the model started 5 years ago. So from today, 34 years, but from 5 years ago, 39 years. So we may be able to save them. Okay.
I get the 100. I get 100.
Okay.
1400.
Once the population drops below 100, the situation will be irreversible. When will that happen? Better? Yeah, it was given to us. Perfect. Okay, now we're ready for something else. 30. On the same page, 530. Let's read the problem. The half-life of aspirin in your bloodstream is 12 hours. Half-life, 12 hours. How long will it take for the aspirin to decay to 70% of the original dosage? To 70% of the initial. So let's read the problem one more time. Ready? The half-life of aspirin. So I swallow aspirin right now. I'm not even telling you how much. Maybe 100 milligrams, maybe 200 milligrams. It doesn't matter how much. I swallow an aspirin right now. 12 hours later, in my bloodstream, I still have half of it. Let's say I get 100 milligrams. In 12 hours, I still have 50 milligrams. In 12 more hours, I still have 25 milligrams in the bloodstream. In 12 more hours, I still have 12.5 milligrams in my bloodstream, and so on and so forth. Eventually, we hope it goes away. That's the half-life. Okay, how long will it take for the aspirin to decay not to 50%, not to 0, but to exactly 70% of the original amount I took? So if I took 100, in 12 hours I still have 50, but I'm not interested in that. I'm interested to see how many hours are needed for the 100% to drop to 70%, not to 50, but to 70%. So obviously it has to be a number between what and what. If in 12 hours it drops to 50, obviously it has to be between 0 and 12, because it drops only to 70, not all the way to 50%. Okay, so this is a radioactive decay situation. We have to write the mass of T equals the initial mass, e to negative KT. You will be given the model. I mean, this formula will be given to you. Okay, well, we have several situations happening, several ideas here. One, I do not have the initial mass. No one told us how much we took. Okay. We do know, however, that the amount we took in exactly 12 hours, it will become how much? Half. So can anyone give us a point that represents that situation? So I'm telling you I took aspirin right now. I'm not telling you how much. But we know for sure that in 12 hours, the amount that I took will become half. Give me that point. 12, comma, excellent, comma what? I took M0. I took M0. In 12 hours, what will happen to M0? Exactly. M0 divided by 2. That's the point. So I took M0. I don't know how much. You can create that point too. This is the point, the initial point. At moment 0, right this moment, I took M0. Times 0, M0. In 12 hours, M0 becomes M0 over 2. Do we agree with these 2 points? Okay, so then let's show me how we put this point in the model. Excellent. M0 over 2 equals M0 times e to negative k multiplied by? Indeed. Great job. Very good. And now you can say you still don't have M0. I don't care because I can simplify it. I'll simplify by M0 both sides. I'll divide both sides by M0. No one cares how much I took. So then the left-hand side is 1/2 or 0.5, and the right-hand side is e to negative 12k. Oh, that's all I needed. What do you think we're after right now? What are we trying to find? Indeed, the radioactive decay rate. Excellent. How do I do that? What type of equation is it? Good. So what do we need to do? Very good. Natural log, indeed, natural log 0.5 equals negative 12k, and k natural log 0.5 over negative 12. So that gives us k. Is that enough? No. Just looking to see I don't want to exceed 50 minutes. Okay. So we have natural log 0.5 and divide everything by, in parentheses, negative 12. So the decay rate is 0.0578. So here's our model. M of t equals M0, who no one knows, and we don't care about, negative 0.0578 t. And now we can answer our question. One more time, the question is asking, how long will it take for the aspirin to decay not to 50%, but to 70% of the original amount? So what do I have to write? What is this? Say again.
Did you put to the T?
This is what I'm trying to determine. 0.7 times M0. 70% of the original is 0.7 times M0 equals what? Of course, M0 e to negative 0.0578 t. Of course, I'll simplify both sides by M0. I don't have it, and I don't even care for it. And then, as a check, should it be more than 12 hours or less than 12 hours? Of course, very good. So we have 0.7 equals e to negative 0.0578 t, and we will determine the time needed for whatever amount of aspirin to become 70% of the original. Because 50% of the original, we know it's 12 hours. So what do I need to do? Very good. Awesome. So natural log 0.7 equals negative 0.0578 t. So t is the ratio of those two. Excellent. So natural log 0.7 negative 0.0578. So let's look at the calculator and see what we get. So natural log of 0.7 divided by the previous answer, but minus the previous answer. I got 6.17. Does it make sense? Yes. So it's approximately 6.17 hours. So initially, I take aspirin right now. It's 100% of what I took. In 6.17 hours, it will be 70% of what I took. In 12 hours from this moment, from right now, it will be 50% of what I took. Questions for me?